In this video, we're going to discuss transition metal naming. So transition metals are this center block of the periodic table, from element 21 through 30 and down. So we've got lots of different elements that fall into this block. Transition metals are a little bit different than all the other elements in terms of their ionic nature. So when we had things like magnesium, or sodium, or potassium, or calcium, anything in those first two columns, we knew what their charge was. It is +1, it is +2. Way over here in the anions, we knew what their charges were. They are -1, -2, -3. And these are very, very set. If you were to find any of these elements in an ionic compound out in nature, they would have these charges. The idea is long ago in the history of the Earth and the cosmos, the atoms had interacted with each other, they'd already exchanged electrons, and they've been floating around as ions ever since. Transition metals, however, while they have done this as well, the difficulty with them is that they don't have a set charge. If you were to dig up iron chloride. So let's pull some iron here, Fe. Fe, Cl2, and Fe, Cl3 both exist. Depending where on Earth you mined it from, you would get different concentrations of chlorine attached. What's really happening is that one of these has an iron with a 2+ charge, and one of these has an iron with a 3+ charge. Unlike our first two columns of the periodic table, the alkali metal and the alkali earth metals, the transition metal block has variable possible charges. So we need to know which one it is. It makes a massive difference if, say, you're a steel factory and you order a bunch of iron chloride and you get the iron 3 chloride. Well, if you order 1,000,000 pounds, some of that weight is the chlorine. If I order 1,000,000 pounds of the iron 2 chloride, well, the difference is I have less chlorines. So more of my weight is actually iron. Where when I have more chlorines, 1 in 4 atoms, less of my weight is iron than when it's 1 in 3 of the atoms. So how much iron you're going to produce, how much steel you can make, how much profit you'd make, all of that would be wildly different. And on top of it, the different charges react differently. You need different chemicals to react with them to change them into whatever you want. And so this is rather important. We need to know which version of which metals we have. So how do we name transition metals? There is an old name, and we'll cover it briefly at the end, but there is a modern system for naming transition metals that is wonderfully straightforward. It's a wonderful update to modern terminology. If you have an iron, which is Fe, and it has a 2+, you call it iron, and then in parentheses you use Roman numerals. So 2. Remember your Roman numerals: 1, 2, 3, IV is 4, V is 5, VI is 6, VII is 7, and realistically you're not going past that. We use the Roman numerals in parentheses to tell the charge on the iron. So when we had FeCl2, well, you name the cation first. This is, if we want to balance it, I've got a Cl-, I have a second Cl-. My anions are giving me 2 negatives total. I need 2 positives, and I have a single iron to put them on. So it must be iron 2+. We call it iron 2 chloride. Now again, remember that 2 is the charge on the metal. It's not telling you how many chlorides you have. Because if we had FeS, well, FeS A sulfur, if it's an anion, we expect to be 2-. If we go back and look at the periodic table, sulfur is in the column here with oxygen. We expect all the anions to be 2- in that column. So our sulfur should be 2-. I have 1 iron to get my positives on, and I have to be neutral overall. So my iron must be a 2+ to balance the 2-. This is iron 2 sulfide. So again, the 2 here is, as it was before, talking about the charge on the iron. We only have a single sulfide in the formula. That 2 is the charge on the metal. Whereas it makes a difference then when we had FeCl3. Well, how would we name that? It's going to be some type of iron. It's going to have a charge. The anion is a chloride. But what charge is on the iron? Well, each chloride is a -1. So if I have 3 of them, I have 3 negatives. I have to balance my charge in my formula, so I must have 3 positives. And I have only a single iron to put them on. So it must be a 3+ iron, so it is iron 3 chloride. This can get a little more complicated if you have various charges. So let's try to work backwards from iron 3 sulfide. Well, I have sulfides. I must have a 2- sulfur. And I was told iron 3, I must have Fe with a 3+. But if I pair these two together, that's going to leave me with an extra positive. Remember, your ionic formulas must be neutral. So this is not a 1-to-1. So I need some more negatives. But the only place I can get them from is my sulfides. So all I could do is add another sulfide. But if I tried to have FeS2, that's going to give me an extra negative. I'm going to have 4 negatives and 3 positives, so that doesn't work. So I need some more positives. Well, the only place I can get them is from iron 3+. At this point, though, I have 6 positives and 4 negatives. So if I tried to make Fe2S2, I'd be 2 positive. That isn't neutral. We keep going back and forth like this. We say, well, I need more negatives again. So S2-. Well, here, this gives me 6 total negatives, and I have 6 total positives. This is balanced. Fe2S3. So our iron 3 sulfide is Fe2S3. I need 2 of my cations for every 3 of my anions for the charge to balance. Let's try a few different elements too. Let's do vanadium. Because vanadium has lots of interesting properties. You can be vanadium 1, vanadium 2, 3, 4, and 5. All 5 possible versions exist. So let's try them for a bit. Let's try vanadium 1 sulfide. Well, this would give me a V with a plus, V for vanadium. A sulfur, well, as an anion, sulfide, 2-. I'm going to need multiple vanadiums. So I'm going to need V2S. Bring it up to vanadium 2 sulfide. In this case, I've got a 2+. My sulfur has a 2-. Well, they balance out. I need 1 vanadium and 1 sulfur. Vanadium 3 sulfide. In fact, let's pause here and let's try the next 3. Do your vanadium 3, your vanadium 4, and your vanadium 5 sulfides. See if you can identify the formula they would balance out to. Go ahead and pause. All right, if you're back, well, vanadium, I got vanadium 3 plus, sulfur 2 minus. Well, this is much like the irons up above. It was a 3 plus and a 2 minus. The ratio ends up being the same. I need 2 vanadiums and 3 sulfurs. For vanadium 4 plus, well, I need more negatives, and if I have 2 sulfurs, I'll have 4 total negatives. So this is vanadium S2. And if I get up to vanadium 5 plus, well, this one gets a little more complicated, but you end up having 2 vanadiums and 5 sulfurs. And so you can have a lot of different mixtures of vanadium and sulfur depending on which charge your vanadium carries. And again, it just kind of depends on what part of Earth you dug it up from. The local geology, the geologic history changes what mixes with it, what it was exposed to, and therefore what charge it has. One thing you might have noticed here at this point, though, there's actually an easy way to figure out what those subscripts in our formula are going to be. It's going to be the number equal to the opposite or ion's charge. The 2 minus of sulfur became a 2 vanadiums necessary. The 1 charge of vanadium became a 1 sulfur necessary. In our next one down, we see a 2 and 2, which realistically would be vanadium 2, sulfur 2, but we always want the lowest whole numbers for an ionic formula. So divide by 2, it's 1 to 1. If we go down here to vanadium 3, I needed a plus 3 on my vanadium, and I ended up with a 3 sulfurs in the formula. I needed a minus 2 on my sulfur, and I ended up with 2 vanadiums. This cross relation, the charge of one ion is the number of the other ion in the formula. This is always true. The only complicating factor would be when you need to go down to the lowest whole number. So if you ever have a ratio that you could divide into a smaller whole number, we always write them as the smallest whole number. So that's going from names to formula. Let's do a little bit more formula to name. In this case, let's have MnO2. In this case, Mn is manganese. There's going to be some charge on it. And O2. Well, it's not a polyatomic ion that we know. That's just oxygens. There happens to be 2 of them. These are O2 minuses that I have 2 of. So these are oxides. What this tells us is, well, if I have 2 oxides, I have a total of 4 negatives. I need 4 positives, and I have a single manganese to put them on, so it must be a 4 plus. So this is manganese 4 oxide. Now, if you had Mn3, PO4, 4. What's going on here? Well, I've got manganese again. It's going to have some charge. And, well, I have in these parentheses PO4. Now, if you think back to our polyatomics, PO4 is our phosphate. And that is a PO4 with a 3 minus. So I have phosphates. Well, if I have 4 of them, PO4, 3 minus, then my total negatives is 12 negatives, which means I need 12 positives. So if I have 12 positives and I have 3 manganese to put them on, I spread those positives out over all of my manganese. So 12 divided by 3, that's 4 pluses each. So manganese here is a manganese 4 again. Manganese 4 phosphate. Nothing in the name tells you how many of the different ions you have. We are left to figure that out by using known charges of the anions to determine the charge of the cation. All right, in terms of naming transition metals, that'll be enough examples. We'll have a practice video up as well.